Hello, today I will be discussing Lab 3, the magnetic field of a bar magnet for Physics 2212. I will begin with an introduction that explains the overall problem and results found, as well as the fundamental principles involved in the experiment. Then, I will discuss the data, which includes the calculations made, the code used, and the model created, and finally, I'll end with a conclusion focusing on discussing the sources of error involved in the data measurement process and a few discussion questions. Going into the introduction. The goal of our experimentation was to determine the distance dependency of the magnetic field by comparing the value we calculated to the value given in the actual formula. We calculated this value by using a magnetometer app on our cell phone to calculate the magnetic field at different distances, and then graphed the natural log of the average of the magnetic fields against the natural log of the distances to find the constant value, which we compared to the value of -3 as given in the original formula. In my findings, I found the value to be -2.3, the possible reasons for which I will describe at the end of this video. The primary fundamental principles utilized were the on and off axis formulas for the magnetic fields, which allowed us to create the arrows given in the model depicting both scenarios, and find the magnetic field in both scenarios. Additionally, the principle we are investigating, as I mentioned earlier, is the distance dependency of magnetic fields and the comparison of actual and theoretical values. Superposition is also involved, but mainly in the discussion questions. Now advancing to the data collection. As I noted earlier, we calculated the average of the magnetic field at various distances, which can be seen here. I will highlight a source of error here, as for the latter two R1000 trials, I was unable to find a value closer to 1000 Teslas, or microteslas, which could throw off my distance measurements. Moving on, you can see that the n value I found was approximately -2.3, which is not as close to the expected value of -3 as I had hoped. Last in the calculations, you can see that I used the formula of B equals mu0 over 4 pi times 2 mu over r cubed to find the magnitude of the magnetic dipole moment at each observation location, which I then averaged to find 0.8 as the final average magnitude. I plugged this magnitude value into the code and then used it in the shown functions. As you can see, the top function has the formula for the magnetic field of the dipole, the middle code snippet depicts the scale used, and the last bit shows the magnetic field of the dipole along a 45-degree angle, for which I multiplied the x and y components of the distance vector by the cosine and sine of pi over 4 radians respectively, as these are equal to approximately exactly 45 degrees. As you can see, this is the model generated by running the code. The values for the magnetic field are given at the bottom, with the off-axis magnetic field having a value of 1.54 times 10 to the -3 in the x component, the on-axis value being -7.705 times 10 to the -4 in the x component, and the 45-degree magnetic field having the value of, in the x component, 3.85 times 10 to the -4, and in the y component, 1.15 times 10 to the -3. Which I compared to the observed value of 2.96 times 10 to the -4 in the x component and 8.3 times 10 to the -3 in the y component Teslas. Finally, delving into the conclusion. I would like to take some time to highlight the sources of potential error in this lab, as there were quite a few opportunities to make a mistake. I already mentioned one earlier, which was the difficulty I had with finding a proper R1000 value, which could have skewed the later measurements, as they were all based on that initial one. Additionally, it was difficult to lock down a number for the magnetic field, as the magnetometer was fluctuating quite a bit, even when I let it sit there for a while. Therefore, I picked a number arbitrarily in the range of numbers that were showing up, which could have caused inaccuracies. Furthermore, the presence of nearby objects could have easily influenced the magnetometer readings. Although I did my best to stay as far away from other magnetic objects as possible, it is still completely plausible that the field from my laptop, TV, radio, computer, or some other appliance impacted the measurements. Finally, the app itself could have had some data inaccuracies. As was mentioned in the lab handout, our cell phones are not the best or most accurate magnetic field data collectors, and I do think that could have impacted my results. Moving on to the discussion questions. As we can see, the first question is what would happen if we had not oriented our compasses and magnetometers to compensate for magnetic north. I think that our components would vary because the Earth's magnetic field wouldn't zero out, and this would include the principle of superposition as it would affect the net magnetic field. The second question is a scenario in which we were to stick two identical magnets together end to end and repeat the experiment. This would make the magnetic fields twice as strong as we would have two magnets involved. Thanks for watching. That's it for Lab 3.